So the Navy Global Ocean Prediction System runs every day on a 12-degree tripole grid. It's been operational since late 2018. And if you go to hicom.org, you can get redirected to NRL for images and movies. Or you can download the actual model fields from our data server. It's 41 layer HICOM coupled to size 4 for sea ice. So HICOM was the first widely used AL-based ocean model, but it's 20 years old. And lots of the code is still from an even older MICOM code base. So it really needs a complete refactoring. And some of the changes we'd have to make are high risk. That is, they might break the model. And of course, now HICOM is no longer the only AL-based ocean model. And in particular, MOM6 has modern numerics and coding, a much larger developer base than HICOM. But it's also quite similar to HICOM in many ways. So at COAPS, rather than developing a next generation HICOM, we intend to switch to what we call HICOM 3, which is MOM6 configured to be HICOM-like, and using some of our existing HICOM tools for pre and post processing. And in particular, all the plots I'm going to show in this presentation are from HICOM tools. So for the test case, it's a 10-year simulation using the GOS 3.1 configuration, but without HICOM-specific features. 41 hybrid layers in the vertical with 1 meter top layer. In HICOM, the fixed vertical coordinate is Z sigma Z, which I'll explain later. And in the test case, it's Z star only. And in HICOM, we can have different target densities, for example, say in the Black Sea. But in this case, they're the same target density, ice petals everywhere. We use a KPP mix layer, and we repeat one typical year of CFSR for 10 model years using the large and Jaeger bulk stress parameterization with absolute winds. Some of the differences between HICOM and MOM, HICOM is non-Boussinesque. The equation of state in HICOM for sigma 2 is a 17-term rational function. And in MOM6, we're using the right pressure separable equation of state for efficiency. HICOM is incompressible with a thermobaric correction versus compressible in MOM. The isopycnal regridding in HICOM, we're using layer averages, and in MOM6, we're using layer interfaces as the target. HICOM no slip, MOM6 free slip, and size 4 versus cis2 for the sea ice model. And generally speaking, the parameters are tuned for HICOM and may not be optimal for MOM6. So 10 years with this repeated atmospheric forcing. The snapshots here are in logical array space. So you can see the tripole grid with the Arctic bipolar patch starting at 47 north. And it's hard to see details really in the global plot, but you can see these are broadly similar simulated solutions after 10 years. Both were run on a Cray XE4 on 1800 cores. MOM runs 1.5 times faster than HICOM. HICOM is actually slightly faster than MOM per time step, but we can use a longer time step, a longer baroclinic time step in MOM. In MOM, unlike HICOM, we can also use a thermodynamic time step, which we have set at 1200 seconds. And the speed up is similar to the time step ratio. So the rule of thumb, if the time step is twice as long, then it will be twice as fast. So there's been several presentations about what is AL in the previous webinars. The basic idea is we solve the layer continuity equation, so we move the layers, and then we remap them back to the desired layer structure. The fluid does not move, but the layer interfaces are regridded across the fluid. And the power of the method is in choice of new layer locations. And the method of choice for HICOM is a favor isopycnals approach, where isopycnals outcrop into fixed depth layers near the surface and at high latitudes. And this is an option in MOM6 using its HICOM-like regridding option. And as I discussed briefly earlier, HICOM maintains layer averages at target sigma 2 potential densities. And essentially it uses local entrainment and detrainment logic to calculate how to move the interfaces based on that target. MOM maintains layer interfaces at target sigma 2 potential densities, but with a small compressibility factor to ensure a monotonic density profile. The advantage of that approach is there's a unique mapping from a monotonic profile to the target densities. In the case of HICOM, you can have several different regriddings which give you the same layer target densities, which can cause problems if you don't choose the right one. This is a little bit of an aside because in the test cases, we don't use Z sigma Z, but this is showing the kind of thing you can do with an L coordinate. In the earlier GOS 3.0 configuration, we had 32 layers. One of the things here is, when you're running operationally every day, it's got to run fast enough. And so we tended not to add layers unless we really felt like we had to. So for a long time, we used 32 layers with a 3-meter top layer and 5 layers, always fixed depth. And what we found for that wasn't really optimal for the mixed layer, and isopycnals could upwell onto the shelf. This wasn't wrong in the sense that isopycnals do upwell onto the shelf. The problem is, that you then don't have any structure in the velocity, for example, and that was causing some issues for us. So in GOS 3.0, we added 9 layers and they were all near the surface. And so 14 of those 14 layers now are terrain following. And the schematic shows you how that works. Essentially, the figures are bottom depth on the x-axis and interface depth on the y-axis. And in deep water, essentially, the fixed coordinates are horizontal. They're geopotential. If the bottom becomes 96 meters or less, then you become terrain following. And if the bottom goes shallower than 14 meters, you switch back again to 1 meter Z level coordinates. For the MOM6 HICOM twins, essentially we just use the bit that's deep water from that. That is, we at 96 meters and shallower, we continue to use Z coordinates. We don't switch to terrain following. And in HICOM, there's a separate parameter that can set a minimum depth for fixed, at which you switch to isopycnal. In MOM6 and in HICOM, you can just do that by setting the target density very light. So if a layer has a very, very light target density, essentially it's always outcropped, and therefore it's always at its fixed coordinate depth. So here's a vertical cross-section at 180 degrees east in the middle of the Pacific over the top 1,000 meters and a 3-year mean. And you can see here the lines are the interface depths. And you can see that in the Southern Ocean, in the top 1,000 meters, we're always in fixed coordinates all the way down to 1,000 meters. And even in mid latitudes, we're deeper than 96 meters when we're in always Z coordinates. one takeaway from this is that, in fact, even though we're using a different approach for target densities, these are very similar kind of looking sections. One issue with the algorithm we're using for entrainment and detrainment is that you can get thick, thin layers in HICOM. And if you look at 40 North, you can see that's happening here. Now remember, this is a 3-year mean. So that means those layers that are thin in this plot are always thin. And so essentially they degenerated. We do effectively have less, in that area we have less degrees of freedom than we think we had. This is the same section, but now 1,000 down to 6,000 meters. And in this case, you can see the advantage of the compressibility factor that MOM6 is using, which makes it easier to get layers in the deep ocean. And so here you have more uniform distribution of layers in the deep ocean in MOM6 than in HICOM. So this is comparing HICOM and MOM to global drifter eddy kinetic energy. The lowest two plots are the same plot, and therefore drifter EKE over 30 years. And the top two panels are 3-year means from the models. And again, you can see in broad outline that the strong currents are represented similarly in the two models and in the data. One difference is that when you look at the areas with low EKE, the drifters, that's about 14% of the global area between 67 and 60 North. In HICOM, it's about 19%, and MOM, it's 26%. So away from strong currents, MOM is giving us less EKE. Because the drifter EKE is 30-year average, so it's got lots of interaction variability, it's hard to know what the right answer there is, whether, you know, HICOM or MOM is doing a better job for that, unfortunately. This is a cross-section for the equatorial Pacific. And this is the only area where layer 15 is isopycnal. Remember that layers 1 through 14 are always at fixed depth. And an issue with isopycnal models is you have to represent all the densities that you can see in the global ocean. So in this case, layer 15 is representing essentially just this little piece of the West Pacific. Everywhere else, essentially, it's in Z coordinates. HICOM's equatorial undercurrent is too weak. MOM's might be too strong. It's in the right ballpark, and it might be slightly too deep. But I think there's no doubt here, looking at this picture, that MOM is doing a better job in this region. So I mentioned earlier that HICOM is incompressible with a thermobaric correction, and this approach can be unstable. And even if it's not formally unstable, it can be noisy. MOM fixes this problem by integrating the finite volume pressure gradient using a numerical quadrature. And a simple way to look at thermobaric instability is to plot the difference between snapshots 12 hours apart. And what you see on the left here is the surface signature of what's almost certainly thermobaric instability in HICOM and not at all in MOM6, which you know, would be expected from the theory, but it's nice to know that that's true in practice. Alistair showed a similar result for other MOM runs, but the Atlantic overturning stream function from MOM seems to be shallow. Now, HICOM's stream function isn't perfect, partly because it has a hard time when it's using purely sigma 2 representing the Antarctic bottom water well, but it's clearly deeper At 26 North, for example, it's 3,500 meters where you get the zero transport crossing versus 2,730 meters for MOM 6. And when you see a shallow Atlantic overturning, one thing to look at is overflow from the Nordic seas. And here's a plot of 3-year mean bottom density, bottom sigma 2 potential density from HICOM and MOM 6. And MOM 6 is significantly less dense at the bottom than HICOM. Now the black bar on the HICOM plot at the lower left is a section I'm plotting in the next slide. This is probably the largest difference between the 68 sections we routinely make. The other one that had a large difference was the equatorial undercurrent I showed earlier. So this is across that section as I showed you. MOM 6 has lost left 38 and is further from climatology than HICOM. And there's almost no salinity variation here in MOM 6. So one of the things we care about when we're doing these high resolution runs of the western boundary currents, when we do a simulation, the assimilation can correct for some deficiencies in the location of these western boundary currents. But if your model doesn't represent them accurately, as soon as you go into forecast mode beyond the assimilation, it starts reverting back to the wrong state in some sense. So we'd like to have a good representation of the western boundary currents as we can. And in this case, the black lines here are the mean location of the Gulf Stream plus or minus a standard deviation. And you can see near the US coast at about Cape Hatteras, there is no variation in the location of the Gulf Stream. And HICOM is consistent with that. HICOM is separating at Cape Hatteras as it should, although it's slightly too far south as it enters the rest of the domain. On the other hand, MOM 6 is separating from the coast much too early at about 32 north. On the other hand, the Gulf Stream itself seems to be penetrating further east. That is, we're seeing more variability in the east of this domain than with HICOM, and that variability is somewhat realistic. Now, to a large extent, the Kuroshio is easier to get right in global ocean models than the Gulf Stream. There are some states you can get into within the Kuroshio which are not realistic, or not realistic when you get stuck in them. But generally speaking, it's easier to model the Kuroshio. And in this case, both models seem to be doing fairly well on the Kuroshio. And again, MOM 6 is penetrating a bit further into the basin. This would have been easier to illustrate with a movie, but I wasn't sure that was going to work. A problem we have with the simulation is MOM 6 loop current eddies never migrate into the Western Gulf. Looking at this snapshot, which happened to be the same day, there's no reason why they should be the same. It's a simulation. But you can see that in HICOM, an eddy has detached from the loop current. And there's a smaller, and there's an eddy that is still there, which has migrated into the Eastern Gulf. In the MOM 6 case, the loop current configuration is a perfectly reasonable configuration. But in fact, we never get fully detached loop current eddies. What happens is they detach as they should, but then they don't migrate into the Eastern Gulf. They get reabsorbed by the loop current. And if you look at the service height variability over 3 years. You can see that in HICOM. You can see the path that those loop current eddies take into the eastern Gulf. And in the Mom 6 case, there's more variability concentrated in one area, but it never gets into the eastern Gulf. So in summary, I said that Mom 6 and HICOM are very similar models, but of course, Mom was initially developed for climate applications. So how well does it do at higher resolutions and maybe for global ocean prediction? And I would say that the results are broadly similar. The most serious issues were in the Atlantic. In particular, the premature separation of the Gulf Stream is worrying. The non-shedding of the loop current eddies it may or may not be related to the same problem. And of course, we did see also the overturning circulation in the Atlantic was a little bit in question too. We now have an Atlantic-only configuration, which is a bit cheaper to run, which we're using to explore some of these issues. But generally speaking, MOM is still a good candidate for future high-resolution ocean prediction systems. And one of its advantages is it allows the same model to be used for synoptic and climate timescales. I think here by climate, I'm probably meaning climate in the NWP sense, that is, a few months. But clearly, it can also be used for much longer than that. So in other words, it's a simplification for an operational center to have one model rather than two. HICOM 3 is MOM configured to be HICOM-like and using HICOM tools. And I think long-term, there probably won't be a HICOM 3. That is, it really is MOM 6. But it does simplify the transition from MOM 6 for existing users of HICOM. So that's it.
Okay, thanks, Alan. Okay, Enrique had a question.
Yeah, Alan, quick question. When you use the terrain following coordinates, does that put a constraint on the gradients of your bathymetry?
No. One of the advantages of using sigma z is that you're only terrain following in shallow water. So you're not doing the continental slope, which tends to have larger gradients. But generally speaking, we don't try and make the we don't try and smooth the bathymetry to meet some of the criteria you might use if you were using a conventional terrain following model. And conceivably, that's a problem. But we're on the shelf. We're doing a lot of mixing anyway. So we're just winging it in some sense.
Okay, thanks.
Steve Griffiths.
Alan, on slide 4, if you could go there, there's some terminology I'm a little confused about. I just want to get clarified on the use of terminology. I believe you said that the HICOM is non-Boussinesque, but that you use a incompressible with thermobaricity versus compressible. Incompressible versus non-Boussinesque. Non-Boussinesque is a compressible fluid typically. That's the terminology people usually use. So could you clarify that point, what you're talking about there?
So I'm using Boussinesque in the sense of what's conserved. Is it layer volume or layer mass? And essentially in HICOM it's layer mass.
But that means it's a compressible fluid. It's not incompressible. But you say it's incompressible there.
Well, the equation of state is sigma 2.
Okay.
So which to my mind is incompressible, right?
Yeah, it's just a bit confusing, the terminology. Incompressible in the fluid mechanics is typically non-divergent velocity field, whereas a non-Boussinesque has a divergent velocity field. Anyway, that just clarifies my question.
Right. I think I was just saying it's not like the classical Boussinesque ocean model.
Yeah.
Maybe non-booson-esque. Maybe there should be another term for that. But
Okay, thanks.
Other questions for Alan? Alan, I had a question. What kind of horizontal or lateral closures are you using in these cases? Are they biharmonic or
so
something else?
we have both biharmonic and Laplacian.
Okay, and those are prescribed viscosities, or
They're prescribed viscosities, yes,
okay,
and generally they're a function of grid spacing.
right?
In the case of the Laplacian, we use a constant coefficient, but in the case of the biharmonic, it's a function of grid spacing cubed.
Right. Okay, Gokhan, you're up next.
Yeah, I think you indicated that you were going to use the Atlantic configuration to iron out some of the issues. I think that configuration will be okay for the Gulf of Mexico issues, but the any information you get from the Atlantic for AMOC and its vertical extent or whatever will be highly dependent upon what kind of boundary conditions you use on the northern side, and that may not be necessarily translatable to the full global configuration.
Yes, I mean we've certainly seen already that because in fact we're imposing climatology on the northern boundary. It isn't exactly the same as the global model when you look at the overturning circulation, but in the same configuration as the global model, it's somewhat similar. And so it gives us at least a starting point for looking at, what could we change to make it different. And in the end, we have to run a global case. I mean, I agree. I mean, the problem is just the cost involved.
Okay, Dan Witt.
Hi, I see that this is a point of clarification. I see that you're using the large and Jaeger bulk flux parameterization with absolute winds. And I presume that means, you can clarify me if I'm wrong, that you're not considering the ocean currents when you calculate the stress. And I guess I'm wondering why you're doing that, and if you've tried the relative currents or some variant of the relative winds with the ocean currents and found that has deficiencies in your case.
So we're using, so when we run HICOM, we use the core 3 algorithm, not your large and Jaeger, generally speaking. But because MOM actually has large and Jaeger built in, we switched to using that. And generally, when we run HICOM for prediction, we would use relative winds. The problem with relative winds in general is that it tends to dissipate eddies, and so they tend to last less time, and ocean currents are generally less strong. And again, in theory that's correct. That is, but the problem is we're trying to run at essentially a suboptimal grid resolution, and yet still get good answers. And so sometimes you go with a better answer for slightly the wrong reason, kind of argument. I think there's no doubt that if you were running a fully coupled model, you would want to use relative winds. There are some papers out there saying that if you use prescribed winds, then you should either not use relative winds, or you should modify relative winds. So it's a bit of a fuzzy area generally for prescribed atmosphere kind of runs.